Welcome back, PlayBASIC coders. A question came in the other day about how to build a Lexer. And Lexer is short for lexical scanner. You might know it as Tokenizer. So in the context of this brief video, what we're going to be doing is we're going to search through a string. We're going to classify groups of characters as particular types. So alphabetical groups of characters will be tagged as being words. Whitespace will be tagged as being a whitespace. And in this case here, there's nothing else. But you can have other things too. You can have like this is message number 1. In that case there, we would, to represent this in our tokenized format, we would need 3 different things, wouldn't we? We need a word, a whitespace, and a simple number primitive. Rather than talk about it, let's just do it. First, off-the-cuff implementation. So we're going to step through this string here, this variable s, from the first character, so we'll loop in the first character, to the length of $s. So this is our outer loop. And as we step through, we'll read each character. We have a function in PlayBASIC for doing this very thing. And mid returns the character at this position. So strings are a bit weird in BASIC, I guess. They're not zero terminated. They're not zero inclusive. They start from 1 up to the number of characters. So starting from 1 is talking about this character here. On loop 2, we would see this character, loop 3, so forth, all the way through it. How do we classify this thing? Well, let's put some boilerplate at the bottom here. So when we run this thing, it won't run and run off the screen immediately. All right, okay. What kind of things are we going to support? We're going to support alphabetical groups of characters. I'm going to classify those as being a word. And let's just check if this character here is alphabetical. So the easiest way to do that is just comparing it with the ASCII values. You can run through and you could go, hey, are you any of the characters A to Z? In maybe a loop. That's not very efficient. We can just use comparisons here. So we could just go, is our character we are looking at, is it greater than or equal to, or if you like that way around? And this character is lower than or equal to ASCII of lowercase z. This would give us this expression here will return true if this character here is alphabetical and lowercase. That's not the case for all words, though, isn't it? The situations where we need uppercase and lowercase. So I'll just copy the expression. Let's put some brackets around here. We're going to have 2 expressions. And we're going to selectively choose which one we are. If either of these expressions is true, then we'll fall through to the inner code. It's a bit of a mouthful, though, isn't it? So what should happen now is when the character is alphabetical, either uppercase or lowercase, we should be able to just output it to the screen. It's not very pretty though, is it? Yeah, I mean, it's a big long expression. We could probably do that better, I would say. Let's run it though, see what we get on the screen. We get all of the alphabetical characters and nothing else. That's good. That's what we wanted to find out. I'm going to jump ahead and I'm going to make a function out of this. So we'll just go, well, I don't know, is alpha character. I use the same variable, so it's nice and comfortable when I cut and paste this stuff together. Function, our expression. Now we can just wrap all of this into one variable here, make a Boolean expression out of this. And we'll return state at the end here. Now I'm just doing that so we can have kind of a cleaner look to our expression, our main processing loop. Now, if we run it again, we should get the same output. Fantastic. But we're not doing words, we're doing characters so far. So we're only reacting to this. But if I put something in here, that's not a word, a white space or something else. We don't even tackle white space at the moment. Numbers over here, we just get nothing. It has no reaction to that. I think the simplest way of writing a tokenizer or a Lexer is a bit like this. If we scan through, we find the first character. In this case here, we're going to react to characters that are uppercase or lowercase. Now we just need to find where the end of this run of characters is completed. So you could go, well, all right, character loop or something. We'll loop from the current position, which is the outer loop. And we want to loop to potentially the end of this string, because it's possible that this run of characters might butt up against the end of the string, like that. And we're doing the same thing. We're just going, all right, dude. So if is alpha character, and we'll get the character at this position. We've got to make sure that we read the inner loop's character position. If this fails, let's exit. If this equals false, then exit, dude. I'll wrap it into there. Yeah, just wrap it in there, so it's a bit easier to see what's going on. The exit will make it when this condition is met. Control is going to jump from here outside of this end loop here. So this for next loop is this block here. We're exiting that block, not the outer block. Probably the simplest way of doing this is just go, let's just keep a variable, we'll call it end position, that is the last known character, valid character that we went past. I think we'll get rid of the print character there for a second. And we'll try and print the word. So when we think about it, we should, when we exit this loop, in a loop here, we should actually have this end position variable in here. It has to be set because we are starting to loop from the first character. It's a bit of a, look, we're doubling up some work there. Okay. It's not going to kill us, performance-wise. So I think we'll make a variable called this word. We want to grab, using the mid string this time, the characters starting from the loop, which is the very first character, and this end position here. It's a bit convoluted to do that, but we can do it. Our parameters for mid are the string that we are operating upon. This is the position within the string, and this is the number of characters to grab. So it's going to be end position minus loop, and we have to add one, otherwise we'll get one less character. If we print word, we should get a word, but we'll get some other weird stuff, won't we? So look. Oh, that's not right, is it? That's a bit weird. What's happening there? I might just load a bigger font, actually. Load font, I don't know, Courier New or something. And a position index 1, and we'll make it 32. Yeah. We'll make the project window taller. 900 pixels tall. So we go. That's easier to read. Okay. Alright, so we've found the character, we've looped forward, ahead, skimmed ahead and grabbed these other characters. So what's going on? What's happening? Well, at the end of this loop here, we haven't moved this outer pointer or the index to where the last character in here is. The last valid character in there. So that's all we need to do. So we'll go loop equals end position, and that should solve our problem. There we go. Looks a bit better, doesn't it? But it's just reacting to words though. We want to have white space and numbers. So how do you think we solve that? Well, same way. This is for words. Yeah, handles well, we'll call them words, but they can be anything. It doesn't have to be a word that makes any sense. It could just be characters. Handle groups of characters. Groups of characters. What about space characters? How do we do that? If this character equals ASC, one space character. Now, if you're not familiar, the ASC command takes a string input and returns the ASCII character value of that string. In this case here, I'm asking it, give me the ASCII value of the space character, which is 32 if you don't know. Now, what we could do here is have the same in a loop, really, couldn't we? We could go, just scan ahead and do a detection of whether this character we're scanning ahead for is a particular kind of white space. There's two common ones, really. There's a space and a tab character. Now, the tab character is actually ASCII character 9. As an ASCII value of 9. So we could have all the comparisons in here. We could go, oh, yeah, if this equals this, this equals this, or this equals 9, which is the tab character. So space or tab characters. Then our inner loop would run, wouldn't it? And we would loop from this current position through till a completion, but we need a version of this comparison that handles the cases that we want to react to. Let's make a function. Let's call it is white space. So if this character equals, this case here, we want to have a couple of characters we want to react to. Where equals space, or this character is equal to 9. If either of one of those comparisons is true, we'll get a true here. Let's replace it up here. So we just go, use the same variable there for simplicity, but is white space. Looks awfully familiar, doesn't it? funny that. Handle it the same way. We're skimming through, when we find a whitespace character, we're skimming through and we're looking for the end of the whitespace characters. Once we find it, we exit, dump the thing out. So here we'll put whitespace. Word. Maybe the length as well, because who knows how many characters we're outputting there. Because, you know, whitespace here, end of that, whitespace. Let's see how it reacts. Syntax error. No, we don't need that, sorry. We need the length operator there. There we go. So at the start of the string we have 3 spaces. I'll make the screen a bit wider so I can see it. Go to like 1280 or something. Sounds alright. Print the original string on screen. Print S. Click save, run it again. That's our original string. So we've got white space initially, 3 characters up front. The next white space we find is 6 characters in length, so it's in here somewhere. We've got white space in between the words. So this word here is there. Let's put expand this here a bit too. So we'll say word. So the output's a bit more readable. Yeah, there we go. Let's do it. Let's try our matching. So we've got word. This word is this part of the output, followed by a space. We've got a tokenized space. Is space a seems to be working okay. It's good. One last one. I'll make a function for this straight away. Don't want this to get too long. So what do we call it? Numeric character. Numeric character. I'm going to go arrange comparison. So arrange from character 0 to character 9, and that will be it. So handling white spaces for this little block here, and handling groups of characters. What about numbers? Alright then, let's have a look. We've got our function already, so we can just do that comparison. Is numeric character. So if it is, we start reacting to it and we go, okay, let's have a bit of a run of the same basic logic again. Is numeric character. And you'll be horrified to know that's what we're going to do here too. We'll make a string called number. That's going to return the digits of this possibly number. So we'll call it number. Put a number in there. Oh, typo. Number, get rid of the length. Don't really need that, because we can see it whether it's correct or not. Is numeric through there. Click save, run it. Let's check it out. So saying with some white space, 3 characters of white space, and we've got a number that's 1 2 1 2 1 2 3 3 2 3 1 2 1 2 1 2 3 3 2 3. Yep. bunch of white space after it, a word, white space, word, white space. Cool. That is lexical scanner or tokenizer. It's the kind of thing that you would process that you would take place commonly in compiler talk, but it's used everywhere. If you want to do something like make an adventure game, you're probably going to need to write yourself a Lexer at some point. And it's just this. That's all it needs to be. It doesn't need to be complicated. You probably realise by now that these things here could be functions with tables of characters that it responds to. So you just pass it different tables and it gives you back a response. So at this point here, we've just run through, classify the things and dump them out. But what does that give us? Let's make it a little structure. Let's just put it all together. Well, a bit more together. We'll have a bit of a type. We'll call it token. We'll have the value of this thing, and we'll call it token type. We'll have an array, tokens, I don't know, 1,000 of those things or whatever, of type token. Nice and easy to visualize what's going to happen. So as we step through this thing, we'll have a few extra constants up here. That'll do us. Token type, and we'll go, what have we got? We've got a word. This might be, well, token. Yeah, we'll call it token type, that's fine. We've got words, we've got numbers, that should be a different class up here, and what else we got? White space. We actually don't really need white space, but in case you want it. Now you could have other classes in here or token types that represent, mathematical operators or brackets or whatever you wanted to, really. We're trying to keep this small and to the point. Yeah, which is rare for me. Yeah. Let's put have a variable here called token count. It's going to equal 0 at the start of this expression. And as we go through and classify stuff, we just got to do this. We could have a linked list of these things, but sometimes I think it's just kind of easier to see what's happening when you do this. Token type equals token type, we'll say word, and then we'll bump the token count. Right, that's in the wrong place, but we're going to start with a tokens array of empty. We've got nothing in it. Nothing's been declared or defined in each position within the array. What we want to do is end up with an array that has these classifications. We probably need a position there actually, which is just going to be, you can do it two ways, couldn't you? You have the actual string value exported from the original string, or you have its position within the original string and a classification of it. Whatever you felt like, really. Alright, so we've got token array, token index, and this is how we're going to classify anything in the array. So if it's a word, we just need to do this. We've got one other thing there too. We've got the value of the token, which is going to be whatever the string is for this thing. Whatever the characters that met this classification. So there we go. This token is going to be a word. It's going to be treated as a word down the line. This is its characters that's made up of it. I'll get rid of these extra talky bits here in the output, so we don't really have them, because I want to output those at the bottom here. Right, so add this word as token. Bump it, move the cursor across, move the outer loop across, all good. We'll do the same thing for Whitespace. We don't really need Whitespace. We'll do it for numbers next, actually. Yeah, bit of numbers. Yep, same deal. Going to tag it. Going to store the number string. Is that what we call it? Numeric. Yep. Numeric, and the last one is going to be. Add this as token. And Whitespace, add this Whitespace. It's just the comments there. We don't really need to update the comments if the code reads well enough. Whitespace, do a bit of that action. There we go. Quick save, run it again, and we don't see anything. Oh, terrible, isn't it? We've swapped the text output for dumping this data here or adding it to a tokens array. So at the end of this loop, if we had a little loop down the bottom here, the loop equals 0 to, token count minus 1. Well, we'll have an ink selection. So we'll go this dude here for token type. We use our cases that we have, our constants that we've already declared up here. So down to this bit there, isn't that lovely? Just trying to reuse stuff without actually having to type it out again. You can enable explicit too. I would recommend using explicit in your programs. But for things like this, as things get larger, it's very handy to have explicit. Then, just in case the output is something that we don't know, it should never need to be this. I'm going to have a variable called C, and this will be a red color if that's the case. So I'm just going to go ink C and then print out the token value. It's pretty cool. Alright, so what are we going to do? We'll have words. We'll render those ones as, that's green. We'll have words drawn as green. We'll have numbers as, I don't know, what do you think? Blue? Yeah, blue. And Whitespace as basically nothing. Shouldn't do anything anyway for Whitespace. That's right. Wow, and there we go. So we get numbers out as blue. Our words are treated like they are actual words and being displayed as green, and our Whitespace has been displayed as black. It's nothing anyway, so it doesn't really matter. And that, my friends, is how you make a Lexer. So really what we're doing is we're taking this input text and from one big blob of text, and we're classifying it down into smaller blocks that we can then work with to apply grammars to, or in the case of doing something like a text adventure, you would need to do that kind of stuff. But maybe you want to write an expression evaluator, or so you can have scripty kind of things in your tools or in your games or whatever. It doesn't need to be elaborate. This is what the point I'm trying to get to. You can make very simple approaches to do this stuff. Not going to break the bank, and it's not that complicated. Now what I would do here to take this a step further is I wouldn't have these separate loops. I would have an array of all the possible valid characters for each different type. Notice how this loop is exactly the same. Funny that, isn't it? Right, so you could sort of go, all right, it's numeric. I want you to call a function and pass it this array of characters that match this type. So for it to be a number, those characters are pre-selected as being acceptable. Anything else is a rejection, it returns false in other words. And we just return, it either just inserts the token for us or returns the number. Returns the string value of that if you wanted to. So it depends on what level you want those things to apply at, doesn't it? Because these are all the same bits of code. They all do the same thing, right? There's nothing special about them. There's just one difference where we've got the classification of what we're treating these blocks of characters to be. So don't be afraid of it. It's not massively complicated. If you want me to make some more stuff about this stuff, sing out in the comments below. But thanks for listening. See you next time. Bye.